Hello everyone. So in this class, now we are going to be talking about the momentum equation. So far in the previous class, we have already talked about the continuity equation or the conservation of mass. So now let's dive in and talk about the conservation of momentum equation. In this case of the hydrodynamic boundary layer, or that is also known as HBL, hydrodynamic boundary layer, right? So this is the boundary layer, and inside the boundary layer we have the velocity u, small u. In this case, capital U is the velocity of the free stream above the boundary layer. This is the flat plate, as we have already talked about all of those things. So now let's just zoom in into this control volume A, and we know that it has unit thickness or unit depth that is inside the page. If you consider it, you don't see it like this, it's inside the page. So which is having unit thickness or unit depth. So now if I want to look at that more precisely, I am going to see something like this. So let me make it very clear to you. See this A B C D, this is that control volume. Okay, this A B C D, this is the control volume. This is exactly the same thing that you should have seen if you had just seen A B. This point is C and this point is basically D, right? So now this is the control volume A. Okay, so now what is happening here is this mxu is entering through this left face, which is AD, and it is getting out, or we can say this is the efflux. Okay, so this is mxu plus d curly d curly x mxu dx. So we have already talked about it, that how it actually changes, how it happens, like as it has traveled this distance dx, and AB is equal to dx and AD equal to dy. So this is how it is written actually, right? This is only in the x direction. We are actually considering the control volume with a focus on the x direction. We will also develop all the equations corresponding the x direction. Okay, so now there is another thing that is like that is mass my. Okay, that is mass my, this my mass. So this is also, suppose this is mass my, which is suppose, okay, I am telling you, just suppose that this is like this my, but we are not considering that my direction, right? We are not taking into account that y direction. So what is happening here is this my is also being carried out, some of the my. Okay, suppose some of the my was going there, but some part of that my has actually became dominated by the velocity small u, and it has just got out from this CB phase. I hope that I'm clear, right? We are not taking this my into consideration, just we are taking this part into consideration, that the my has got some velocity component u. Because of that, myu has just got in there, and corresponding to the x direction, it has got some changes also, that is myu. Basically this is what you write as it is. Then what you do is ddy. Why ddy? Because the change has occurred with respect to the y direction, right? And you write myu who has been changed, that is this thing, and capital dy. I have noticed one thing, that whatever you see here is actually also here. Here it is in the partial derivative term, here it is in the complete derivative term. This is just an observation, so that you do not make any mistake. This is not the logic, but this is the way how I can, or you can remember that. Keep in mind that. Okay, but the actual reason why it happens, I have already described in the previous video. All right, so now this is the thing, we have already talked about mxu and its efflux, and then this myu and its efflux. This is the influx and this is the efflux. Now there is also viscous forces, right? There is also viscous forces, and that viscous force, we know that viscous force, what is viscosity, and what is the viscous stress or the shear stress tau. Shear stress tau is equal to basically mu du dy, which is the velocity gradient. And if I want to talk about the force is basically nothing but stress times area. How? See, stress is equal to basically force or load applied divided by area. So you can say that force is equal to basically stress into area, right? So force will be equal to stress into area. So this is how you write this, right? I know that most of the students know about this, but it is for those who, in case, have missed that or just so from here now we can say that viscous force will be this mu du dy into dx. What is this dx? What is this dx? This dx is the area. Why this is area? Dx is why you consider it as area, because already dx into 1 will be there. Actually dx into 1, this is going to be the area, because this dx is basically it is having an unit like thickness like this. I'm looking inside of that page, so inside of that page it is something like that, which is having a thickness of 1. So that's why dx into 1 is giving you that area, this area. Like it is actually inside the page, right? I hope you can understand. It is actually inside the page. Consider this AB. It has some thickness inside. So that area, we are talking about that area, which is like if it is AB and if it is 1, then this area is basically this, as this is having value dx. So this is dx into 1. So dx into 1 into suppose meter square if it is in SI. So this is how like we find the area there. So I am just explaining it for those who are having difficulty in understanding this, but most of the people, they have got that, right? So yeah, tau equal to mu du dy into dx. So this is going to give you the viscous force, and this tau equal to mu du dy, this is the shear stress, and this is the force. So that is why you are having this extra area term here coming into the equation, and you multiply that area so that you can get the viscous force. All right, so this viscous force is acting along this direction, like against the x direction, you can say, because it is the resistance of the motion of the fluid layer after layer by layer, right? We know that. And this there will be some other like viscous force that will be having direction in this way, on the top face. So this was in the bottom face, that is AB, and on the top face, that is CD, there is a viscous force. And what is that? See, we are writing mu du dy into dx, right? This term, and this term has changed with respect to y. So dy, who has changed this term? Mu du dy dx into dy. Where from where this dy came? As there is a small curly dy, so here you can get like full derivation. So dy. So like this, I just told you that here what you have, you should also write it here. So this is the way to write it. Okay, so we have already got the like viscous forces also, like in the bottom face, and also in the on the face on the top face. I've got the viscous forces also. So we have ended up getting three things: this mxu, myu, and the viscous force. So, and they are efflux and influx and effluxes. If we talk about influx, this is like whatever going in, and efflux is whatever coming out of that like elementary of that control volume, right? Let me just rub these things. These are not part of the diagram. This were just for like better understanding. Okay. So then let's go. Consider the control volume with a focus in the x direction. Momentum influx in the x direction is m dot mxu, and momentum influx. Okay, so momentum, what is momentum? Momentum is basically like we have studied in class 9 or 10, that is momentum is basically mass into velocity. Am I right? Yes. So mass, what is mass? Mass can be written as d rho u dy. Rho u dy can be written as mass. And velocity, it is basically mass flow rate. So m dot is sometimes written m dot s. So m dot basically means the mass flow rate, because rho u dy you can see that you will end up getting kg per second as unit. So this is certainly the mass flow rate, and velocity is basically u. So just by multiplying the mass flow rate and the velocity u, you are getting the momentum influx. Okay, so how rho u dy, how it is kg per second? Let's see. Rho is basically kg per meter cube, that as rho equal to m divided by v, mass divided by volume, and u is basically some speed, so meter per second into dy. Dy is basically meter square. Why dy is meter square? I have already explained that, right? Because dy is basically representing an area. So from there, and I have explained that thing in the previous video also. So this this is getting cancelled, so you are getting kg per second, right? So this is what we can also notice here. So I hope that it was like easy for you to understand. So momentum influx in the x direction is like rho u dy into small u, because this small u is the velocity. So rho u square dy. I've got that. And momentum efflux, we have already seen that mxu plus curly x mxu dx. So we just put the value of rho u square dy in place of what? In place of this mxu. The value of mxu is already rho u square dy, so we just put rho u square dy, and dx is already there. Now you need to partially differentiate this term rho u square dy. So how you do that? Rho is a constant term. Rho is a constant term, so take that out, and dx is also constant term. Take that out. You can also keep the dx there also, no problem. So rho is just taken out. Rho is taken out, and ddx of u square. So see. So from here I can say that u square, if you differentiate it, 2u ddx of u dy dx, right? So this is how like we can get that, end up getting the equation which is rated which is marked with 2. So we are getting the number 2 equation. So let's get going. Since we are concerned with the momentum in the x direction only, the momentum in y direction is obtained by multiplying the mass my. So momentum influx from the bottom phase, I have already told that momentum influx from the bottom phase is basically myu, this term. Okay, so in this case now we are going to talk about that my, right? So my is basically density. Density is rho, and velocity is basically v, small v, and area in this case is dx into 1. And with this you have multiplied u. So from here you can get rho uv dx, right? So my into u is basically, my into small u is basically rho uv into dx. So here you can see that the momentum influx from the bottom phase, my into u, rho v dx into u, so rho uv into dx. And then momentum efflux from the top phase, that means this myu is like getting in, and like it is having some efflux from the top phase, and that is basically myu plus curly y myu into dy. So we just are putting the value of myu, this is this, and then just putting the values, and then by rearranging and applying the differentiation formula, ddx of u into v is basically u ddx v plus v ddx u, right? This is the formula, name it 4. Okay, so now see that resultant momentum change in the x direction will be summation of the momentum efflux minus summation of the momentum influx. So here we are just adding the momentum efflux. What are the momentum effluxes here? Efflux 4 and 2, they are the effluxes. So I'm just adding equation 4 to 2 plus 4, and then you minus them from momentum influx, which are 1 and 3. So equation number 2 and 4 are added, and minus equation 1 and 3. So we are getting like this equation, this whole equation, if you just copy and paste 2 plus 4 and then minus, this is like 1, and this is just the third equation. Then what you are going to do is basically, so you are going to see that this term and this term and this term are getting cancelled, and okay, so this term is actually not getting cancelled, so do not take this seriously. I have mistakenly like gave that. So now what you are going to get is from here, see, so 2 rho u du dx du dx dx dy. So this term is here, and then you are getting rho u dv dy dx dy. Oh yeah, sorry, this term is also getting cancelled. This term and this term has got cancelled, right? So whatever we have got left, I just wrote there. And then now I have taken in one thing, that I have just this is 2 rho u du dx dx dy. So I have taken 1 plus 1. I have written the same term, like 1 plus 2, like the same thing twice. I have just added them, so you will end up getting the same thing again. Then plus rho u dv dy dx dy plus rho v du dy dx dy, right? I have written the exact same thing. Now take a very close look at the red marks. So red, whatever I have marked with red, I have taken them common with in one side, and then whatever is marked with green, I have taken them common in the other side, plus I have added them. So if I take rho common, I am getting u into du dx, this term, and from here I am getting v du dy, v du dy, v du dy, right? And at the same time, here dx dy is just remaining as it is. And then I have taken common this green terms. That means this rho u I have taken common. This 2 rho u's common here. So I am getting rho du dx and here dv dy. I have taken this common, and dx dy are remaining as it is here. And this equation is basically the continuity equation, so I will get them as 0. This is continuity equation. We have already proved that in the previous video. So this is basically equal to 0. So I am just getting this part, which is rho u, okay, this part. So then I'm also saying the viscous force. So we already know this thing. It's coming from the Newton's law of viscosity. The shear force at the lower face of the control volume, tau into area, then mu du dy into dx into 1. I have said why it is. Then you have got this as the shear force at the lower face, and then shear force at the top face. So I have also explained this, how you have got that. So from here I have just multiplied these two things, so I can write them like that. Then net viscous force in the direction of the motion, I have actually named this equation alpha, and this equation is my beta equation. So I can simply do this, beta minus alpha. So I will just get this equation. So after that I can cancel them too, and I will left with this equation. This is my equation number 6. Okay, this is the equation number 6. So now what is this? This is basically the net viscous force. This is basically the net viscous force, right? And what was my 5th equation? This equation, what is this equation? This equation is basically the resultant momentum change. Resultant momentum change is my 5th equation, and my 6th equation is basically the net viscous force. So now the net force is equal to the resultant momentum change, right? This is the Newton's second law. So from there I can say the net force is equal to net momentum transfer. So I am writing this. This is what? This is the equation number 6. You can see mu. This is equation number 6, and this is equation number 5 from the Newton's second law. I can say that, or fundamentally, right? So now what I am doing is this mu and this rho, I am just taking it here, like just dividing mu divided by rho, and we know that mu divided by rho is equal to nu. I can name this nu. This is the kinematic viscosity. So this mu is the kinematic viscosity, and here d square u over dy square dx dy are both cancelled. So I will be left with this mu, and here u du dx, v du dy. So this is the momentum equation in the x direction. So now it's up to you. You can think that what will be the momentum equation in case of the y. So yeah, so we are already done with this formulation and the derivation. So let me remind you what we have done so far. We have just taken this diagram. Okay, if you can, actually in this diagram I have like written all the things very much clearly, so that it becomes easy for you to understand. If you can draw this diagram, if you can make this schematic, you can easily end up getting the equation, because we are using the Newton's second law, which is net summation of the net forces is equal to the change of the resultant momentum. resultant momentum, right? Change in the moment, resultant momentum, that is called, that is what we know from Newton's second law. Basically this is what we are getting. This mxu is influx, this is the efflux. Okay, so this is the influx and this is the efflux, and this is the influx you can say, and this is the like efflux, or you can say that by from this equation, if I subtract this equation, I will get the net viscous force change. This is what will give me summation of the fx. This is what will give me summation of fx. How? By subtracting this from this. Then what you will do? You will write this plus this minus this plus this, and don't forget to like write this mx in its full form, that is rho u dy, and in this case my is basically rho v dx, and just multiply u with it, and here multiply u with it. Okay, do not forget to like properly write that. So if you just do that, you will get the net momentum transfer, right? So that, like this you can like very easily make it. See, momentum influx, momentum efflux. Then we are also considering the momentum efflux from the bottom phase, from the top phase. Then resultant momentum change in the x direction will be simply momentum efflux, summation of the momentum efflux minus the summation of the momentum influx. Then if you like write all of the things together, like you can just get this equation, which is the momentum transfer, and then you take into consideration this value and this value, and then you just subtract them to get the net viscous force, which is this. Then you just say that this thing is summation of fx is equal to net momentum transfer, so this is equal to this. So after that you just get this equation.